Hey everybody, this is Mr. Beckstrom, and today we're going to go over section 2-1, and this is on measurement, and we're going to be talking a lot about significant digits, which we're going to start with, and then we'll talk about precision and accuracy, and we'll also take a look on how to add, subtract, multiply, divide, and round significant digits, and then finally we'll talk about tolerance and how we calculate that. Alright, so let's go ahead and get started with significant digits here. Significant digits is a number, or the significant digits in a number are those that represent an actual measurement. To determine the number of significant digits in a measurement number, we follow these rules. So now it kind of looks like a bunch of rules, but the idea here is that we're only using the places in the measurement, in that actual value that we're using for this measurement. Whether or not that helps or hurts, go ahead. It doesn't look like my camera's working. Hold on. All right. So let's go ahead and just get started off. I'll do an example, and then I will have you do a couple of examples and see how we do here. All right. So the first number is 1050. So if we want to see what are the significant digits here, we're going to see, well, which ones are we really using for this measurement. Now, this is a little bit tricky because you might originally just look at it and say, hey, we're using four values. We're using the thousands place, the hundreds place, the tens place, and the ones place. However, if we have a whole number, we only count the zeros to the right of the number, that would be this 10 here, if it is marked with an overbar. See rule 2C there? So if we have a whole number, that's a number that's not a decimal number, and we have any zeros on the right, we don't count those. Why? And this is the example that I like to give. If I asked how many people were in the United States, and you told me that, well, I think there's about 330 million people in the United States right now. And I said, oh, okay, well, if we just had a new child born, would that mean that we would have 330 million and one people in the United States? And we might think about that for a second and decide that doesn't really make sense. And we decide that really doesn't make sense because when we told you the number of people, we only rounded to the millions place, right? We only rounded to the millions place. So when you talk about 330 million, so let me go ahead. 330 million. Right? We were thinking, yeah, this is, maybe we rounded to here, or maybe we rounded to here, maybe the 10 millions place or the millions place, but we definitely didn't round, or we didn't use any of these values here in our calculation, right? It could have been much more accurate, 331,256,742, then that would have been much more exact. But a lot of times when we give values, we only give it to a certain place there, just like when we talk about the population of the United States. So now what if they did this? What if they did that? That means that they would actually have counted all the way down to the hundreds place, so then we would have had 1, 2, 3, 4, 5, 6, 7 significant digits. All right, so using that, we always count a 0 if it is between two significant digits, and anything that's not 0 is a significant digit. So the 1 and the 5 are significant digits. The 0's between it, so it's significant. And then we measure any zeros at the right end of a decimal number, but this is not a decimal number. And when it's marked with an overbar on the top, this is not marked with an overbar. So this 0 here is not significant, and it clarifies that in rule 3. It says it's not significant when it's at the right end of a whole number. So this would not be, just like these two would not be over here. All right, so there is three significant digits, the 1, the 0, and the 5. These three here in this first value. All right, let's go ahead and I'm going to give you another one, and you try to use the rules and see what you can figure out here. All right. How about 0.005081? All right. Take a minute, use the rules, see if we can decide how many significant digits there are. Pause the video and unpause it when you're ready. All right. So looking at this, I know the 5 and the 8 and the 1 are significant because digits other than 0 are always significant. So far I have 3 numbers. I know this 0 is significant because it's between 2 significant digits. So now I have 4 significant digits. And if I look over here, a 0 is not significant when it is at the left end of a number. So all 4 of these zeros here are not significant. So my answer is 4. That's it. All right, let's take a look at another example here. Let's see, how about 5003 000. And I am going to put a little overbar right here. All right, so pause the video and then unpause it when we're ready to give it a try. All right, so far we have 2 significant digits here because we have the 5 and the 3. Digits other than 0 are always significant. These 2 here are significant because they're between 2 significant digits. So far now I have 4. So really it's just looking at these last 3 zeros. Well, a 0 is significant when it is marked as significant with an overbar. So this one is significant. And that makes this 0 significant now because now this 0 is between 2 significant digits. And the only one that is not significant now would be this last one. So 1, 2, 3, 4, 5, 6. 6 significant digits in this one. The only one that's not significant is this last one because it is at the right end of a whole number. All right, so there's lots more exercises in the book in the first part of this, and so take a look, especially if you're still a little bit having trouble with it, and then I'll answer any questions for you. Just post them in the section forums there. So let's go ahead and take a look at accuracy and precision. All right, the precision of a measurement number is indicated by the place value of its rightmost significant digit, and the accuracy of a measurement number refers to the number of significant digits it contains. So the accuracy, we've really done that already, right? We're counting the number of significant digits in a value, and that would be its accuracy. So for example, if we had the number 3210, we've already figured out that there's 3 significant digits because the 0 at the right end of a whole number is not significant. So therefore, the accuracy would be 3. Now the precision of this is indicated by the place value of the rightmost significant digit. So if you start from the right, this is not significant because we've already decided that because of Rule 3a. And this one is significant because of Rule 1. Digits other than 0 are always significant. So this 1 would be the rightmost significant digit, and that's in the tens place. So remember, we have 0 place, or excuse me, ones, tens, hundreds, thousands going this way. And going to the right-hand side, if we were to go that way, we start with tenths. So tenths, hundredths, thousands, 10,000ths, 100,000ths, millions, and that is going that way. All right, so that is the difference. So let me give you a value, and I'm going to ask for both its accuracy and its precision. All right, how about 0.00560? So I want you to look at that, pause the video, and then I want you to figure out what is the accuracy and what is the precision. All right. Well, looking up here, we're going to first figure out the accuracy. So we know that zeros on the left of a number are never significant, so we never count these 3 zeros here. The 5 and the 6 are because of rule 1, and this 0 is because of rule 2b, right? A 0 is significant when it is at the right end of a decimal number, and if it has a decimal in it, that makes it a decimal number. So here we have 3 significant digits, so the accuracy would be 3, and the precision is the place of its rightmost significant digit. So starting from the right over here, this 0 is significant. So that is the place that we're going to figure out. So this is going to indicate the precision. So remember, we start with the decimal place, and then we have tenths, hundredths, thousandths, 10,000ths, 100,000ths. So this would be precision of the 100,000th place. 100,000th place. All right, let's go ahead and move on. Try some of these. They are starting on page 94 in the book, and they'll give you some examples, and then they'll give you your turn, and see how you do. All right, we talk a little bit about tolerance here as well. And it says very often the technical measurements and numbers shown in drawings and specifications have a tolerance attached so that you will know the precision needed. For example, if a dimension on a machine tool is given as 2.835 plus or minus 0.004 inches, this means that the dimension should be 2.835 inches to within 4 thousandths of an inch. Because remember, the rightmost significant digit of this 0.004 is going to be the 4, and that is in the thousandths place, right? Tenths, hundredths, thousandths, and that's where we get that from. In other words, the dimension may be no more than 2.839 inches and no less than 2.831 inches. These are the limits of size that are allowed or tolerated, right? And we're going to figure out how they found those two values, and it's really easy. You just take your calculator, and oops, trying to shrink this a little bit. There we go. Take your calculator, and to get the lower limit, we're just going to take that 2.835, and we're going to subtract that 0.004. So the lowest value could be is the 2.831, and then the highest value it could be is we're going to take that 2.835, and we're going to add that 0.004. And you can put 0 in front of that decimal place if you want to. It works just as well either way. So the highest dimension it could be would be 2.839. So let me give you an example, and I want you to tell me the precision of our value and also the upper and lower limits here. So, all right. So let's say we have 30.52 inches. So this is what some length needs to be, and it has to be plus or minus 0.02. All right, so take a look at that. I want you to tell me what the precision of this is, and then what the lowest value and the highest value can be. So pause the video and try it now. All right, well, the precision is the rightmost significant digit of this right here, which would be the 2. So that would be in the tenths hundredths place. So that would be precise to the hundredths place. And then to find the two values, I'm just going to take this 30.52. And let's see, that's 0.02. So if you take the 30.52 and we subtract the 0.02, that'll give us our lower limit, which is 30.5. And when we do it, 30.52 plus 0.02, it's going to give us an upper limit of 30.54. 30.54. And that's it. That's it. All right, and the last two things I wanted to talk about is when we are adding, subtracting, or multiplying, or dividing a number, how do we figure out how to round our final answer there? And so we have some rules. We always round to sum or difference, that's adding or subtracting, to agree in precision with the least precise measurement being added or subtracted. We'll take a look at an example of that. And then always round a product or quotient to the same number of significant digits as the least accurate number used in the calculation. All right, so let's first take a look at a sum or a difference and see how we would round the final answer. So let's say I have 30.14 minus 10. How would I round my final answer here? What would that be? Well, if I were to put this in my calculator, and we did 30.14 minus 10, and we're going to get 20.14. So right now I have 20.14, but now I have to round this. And I got to figure out where I round this to. And it says to agree in precision with the least precise measurement being subtracted. So the least precise would be the one whose rightmost significant digit is the greatest, right? So here, the rightmost significant digit is in the hundredths place. And here, the rightmost significant digit is actually only in the ones place, right? Because this is a whole number, and on whole numbers we don't count the right-hand zeros. So this value is far more precise than this value. I'm sorry, this is to the tens place. Did I say ones place? This is to the tens place. The 0 would be in the ones place, but the rightmost significant digit is in the tens place. So that means we are going to round this number here to the tens place. So this would be equal to 20, right? Because we're rounding to this place right there. All right, let me give you one and see how you do. So what if I did 50.7 plus 13.3333? What would the answer be? So try it out and then we will take a look at it. All right, so the first thing I would do is go to my calculator here and say 50.7 plus 13.3333, and I get 64.0333. Now I look to see which one is least precise. Well, this one is tenths, hundredths, thousandths, 10,000ths. So the 13.3333 is precise to the 10,000ths place, whereas the 50.7 is only precise to the tenths place. So this is the least precise number, so we would do this to the tenths place. So this would be 64.0. We would round to this place here, the least precise of our first two values. All right, so let's take a look at multiplication and division. I'll do the first example, and then I want you to try one. What if I did 84 times 5? 84 times 5. Well, I go to my calculator, and I do 84 times 5, and I'm going to get 420. So this is 420. However, always round a product or a quotient to the same number of significant digits as the least accurate number used in the calculation. So this has two significant digits. This only has one. So this answer would be rounded to only one significant digit. So we would only use that first one there. So this would be 400 if we were using these rules. All right, go ahead and try this one and make sure you use your calculator for it too. So 0.003 times 856. Try that one and then we'll go over it. Pause now. All right, let's take a look. First thing I'm going to do is go to my calculator, and we're going to do 0.003 times 856, and I get 2.568. So this is 2.568, but then we have to round it to the number of significant digits in the least accurate of these two numbers. Well, this one has 3 significant digits, but this one only has 1 significant digit. Why? Because we never count the zeros on the left. So we're only going to round this one to 1 significant digit, which would be that first one. So this would round to 3 because the 5 makes it go up to the next number there. So this would just round to 3. All right, everybody, that's it. If you have any questions, please let me know. And I hope you all have a great rest of your week. And thank you.